Thank you so much. Good morning, everyone. The purpose of these presentations is to show how we can efficiently use brain-inspired high-dimensional computing to design a set of efficient learning and classifications algorithm for various applications. Specifically here, we focus on biosignal processing to design classifiers for EMG, EEG, ECOG, generally EXG signals. Well, brain-inspired hyperdimensional computing is all about computing with high-dimensional vectors as opposed to computing with numbers. The information is distributed in a high-dimensional space, and it supports a full algebra. It has a set of excellent properties. First of all, it's very general and a scalable model of computing. You will see a couple of examples here. It supports a well-defined set of arithmetic operations. So essentially, the learned code is analyzable, or you can do essentially transparent learning, if you will. And it does fast and one-shot learning. So we do not need to do back propagations and generally less biologically plausible algorithms here. And for the hardware, it has also very good news. Every operation is almost local, and we can easily implement it in a memory-centric fabric and exploit parallelism there. It is really resilient regarding the noise into the fabric and also noise into the input data. So putting all these together, we can essentially overcome with low SNR conditions, signal-to-noise ratio, and reduce the energy consumptions of these kind of learning and classifications algorithm. Well, quickly, I'm not going to go through to the mathematical details but what are these high-dimensional vectors. They are 10,000 very large vectors, holographic, so there is no microcoding, and pseudorandom with IID components. They support a set of very simple arithmetical operations. They are basically localized operations, and three main operations here, multiplications and additions, which are basically from the linear algebra, and there is permutation that takes it beyond the linear algebra. And once we use these operations, we come up with a learned code, and we can compare these learned codes by simple similarity metrics like cosine similarity or Hamming distance if we use the binary code. Here is a simple examples of mapping things or symbols to high-dimensional vectors. Let's focus on 26 letters of the Latin alphabet. So we have from A to Z, for each of which we choose just 10,000 random bits. Here, the inputs are essentially the bipolar, so +1, -1, that they are chosen with their equal probability. And we store them to a lookup table that I call it item memory. So essentially, it's fixed. You just generate them at the beginning of the computations. You have here the low-dimensional inputs. So for example, a character A, you send it to the lookup table, you will get the corresponding 10,000 bits. Because of this high-dimensional space, the two different symbols are almost orthogonal. So if you compute some sort of similarity here, for example, a normalized dot product, A and B are orthogonal to each other. And here is let me just start with the first example that we use this simple arithmetics to do European language recognitions. We have a text, a training text, very small, about 100 kilobytes of the text. We send it to the letters by letters to the item memory, and we will get the corresponding 10,000 bits. And we essentially apply a set of simple component-wise operations to generate, let's say, a trigrams, a sequence of the 3 letters. And then we combine the trigrams across the entire of these 1 kilobytes of the text by using addition operations, because the addition is very good for generating a set or a groups. And then at the output of the encoding, we'll get a 10,000 bits that is representing the entire of this language. So the next step is to just essentially store it to some things like the associative memory. So we store it in one row of the associative memory and provide the label. For example, this language is German. And we do it 21 times across 21 different languages and essentially populate this associative memory. So here is the end of the training. We get 21 by 10,000 learned language patterns. The beauty is that the same structures, or the same algorithm, if you will, that we use for the training can be used also for the testing. For example, here we have 10,000 sentences from another source, and we do exactly the same steps. We send letters by letters to the item memory. We use the same encoding operations. The only difference is that the output of the encoding here is essentially query, because we don't know the source of the language. And we ask the associative memory, please find the closest pattern. And it will find, for example, the highest cosine similarity or minimum Hamming distance, and it will return the language, identified language. It achieves 97% accuracy on par with the state of the art. And then we realized that it essentially forms a generic high-dimensional processing unit with these three main steps. First, in low-dimensional space, or the original space, if you will, we have to do some sort of traditional pre-processing that essentially they can be eliminated. We have seen it, and that's, for example, for lots of these biosignal processing, we can push high-dimensional computing to the raw data, which is a good news. So we get a set of inputs in the low-dimensional space. We do the seed generations that you have seen one example by means of the item memory. And then once we generate these seeds operations, we perform the encoding operations, very local, simple, component-wise operations, and we will get a single 10,000 bits out of the encoding. We store it to the associative memory that finds the closest similarity. And this associative memory can be continuously updated during the lifetime of the operations of the system and essentially form some sort of active or online learning. And then we come back again to the low-dimensional space or the original representations, which is the answer. Here is one extension of the kind of the architecture that I've shown you, but it is totally operating with another set of the input data. It's for the EMG, electromyography data, to use basically to do some sort of hand gesture recognitions. We had here 5 different hand gestures. We get the data from a set of EMG sensors, essentially 8 channels. We do very simple pre-processing. As you can see here, it was based on the US, so we have the notch filter to get rid of the power noise, and then essentially just do a quantizations. But we have 2 different paths. One is the name of the channels that we use the discrete symbols to map them to the hyperspace, and there is another path on top that essentially we use a continuous item memory that maps the analog inputs to a hyperspace. Once this mapping is done, here is the localized component-wise operation that combines or fuses the informations across the channel and, of course, across time, because a gesture has a set of samples over time. The output of this encoding is another 10,000 vectors. We store it to the associative memory during the training, and for the testing, we ask from the associative memory what is the label of this gesture. Pretty much we design a set of high-dimensional architectural templates, if you will, with the same set of principles, but across a wide range of the applications that I listed here. For example, going from one single discrete inputs for the text applications like the language recognitions or news categorizations, all the way to something complex like EEG, brain-machine interfaces, where we had 64 analog low SNR inputs. So in terms of the number of the inputs, the number of the classes, the type of the application varies from binary classifications all the way to 26 classes. And here shows basically the classifications accuracy on average of the high-dimensional computing compared to the state of the art on that given specific applications, ranging from KNN, SVM, DeepNet, for example, for the speech, and some of the also EEG brain-machine interfaces. We managed to essentially build an embedded tiny accelerators that easily scales up to 256 channels and meets the real-time constraint for these types of the applications. Typically, end-to-end classification should be about 10 milliseconds, so you can control a prosthetic hand in EMG and EEG cases. And it is 10 times energy efficient compared to an ARM Cortex-M4, just because of these localized and simple operations. Let me just show you some other benefits from the HD itself. First of all, it learns very fast. We started from the EMG. We use gel-based electrodes. These kind of the signals from the gel-based are quite high quality signals. So this is not a big surprise that traditional techniques like the support vector machines requires more data to be able to reach the good accuracy that we achieved with the high dimensional computing. So here in these examples across different subjects, we've seen that overall SVM requires 3 times more training data. So we learn much faster. Surprisingly enough for the EEG, here brain-machine interfaces, we have seen more or less the same trends, 3 times more trial, but even here we were able to push the HT close to the raw data, so essentially we remove some of the pre-processing like common average reference filtering. And recently, we moved from this gel-based to something very low SNR signals. Here is a flexible EMG electrode array that is essentially like the flexible PCBs. That subject is really comfortable to wear it, but the signal is really noisy because they are not gel-based. But surprisingly enough, we have seen that this shows the learning curve across different number of the trials and the classifications accuracy across different subjects. We truly can do one-shot learning. So just only one single trials per each gesture, we can achieve almost 90% accuracy, which is higher than the state of the art. And this was for training and testing in the same day. If we do the testing on the day after that, which essentially the subject will reposition the flexible electrode, we just lose, about 7% accuracy, and if we do it with the state of the art, is about 50%. The random chance here is 20 because we have 5 gestures. All right, so here I have shown you that how high-dimensional architectural templates can encode different analog signals to form different learning and classifications tasks for various biosignal processing applications. It's fully scalable, and the other good news for the hardware side is that we have identical hardware for the learning and the inference. It does fast learning and operates under low SNR conditions, which can really improve the energy efficiency and also can do continuous and online learning as well. Thank you.
Thank you very much. Very interesting work. So are there questions? Can you comment on your accelerator unit that you...
Yes, so this is essentially a simple embedded 8-core processor. They are risk optimized with some instruction set extensions to do bitwise operations. But it is not basically dedicated hardware. It's a 8-core embedded processor. Yeah.